For those of you who are new here, this is a monthly tech talk series that we structure around unstructured data and large language models. I am your host. My name is Yujian. I give a talk at each one of these because that's my job. And I typically also bring in a couple of other people to give some interesting talks. And so today we'll hear from Damon Abraham and Ollie. I'm going to let you pronounce your last name yourself when you come up. Ollie M. And I'm going to kind of get into the first presentation. Cool. So according to the agenda today, the first thing we're going to talk about is basically pre-processing for RAG. Who here has built a retrieval augmented generation tool app? Yes, I saw yours. Okay, some of you guys have built some. Who here has heard of RAG before? I just said it. Okay, so most of you guys have some idea. Okay, what about vector databases? Who knows what a vector database is? Okay, a small amount. Oh, that's like about half the room. Wow, that's great. Okay, usually I only get about 30 to 40%. So it turns out that the work that I'm doing is having some impact at least. All right, let's get into this. So first, I'm going to introduce myself a little bit. So as I said earlier, my name is Yujian. I'm currently a developer advocate at Zillis. Prior to being a developer advocate at Zillis, I ran a natural language processing API company. I ran that from 2021 until early 2023. Kind of shut it down after November of 2022. I don't know if you guys remember what happened then, but ChatGPT was really popular, and I was like, well, I'm not going to compete with that. And that QR code there is to my LinkedIn. If you want to find me, you can come talk to me on LinkedIn. I post a lot on there. You can see all my events, and you can also listen to my ramblings about how all the AI things you're going to learn here is going to help you knock more than just the socks off your Valentine tomorrow. All right, a little bit about Zillis. So Zillis is a vector database company. We maintain many projects. Primarily, we maintain this project called Milvis, and that's what my shirt says. And Milvis is an open source vector database. We're the only distributed open source vector database. And I believe we are the only vector database with more than 50 projects using over 1 billion vectors in production. And Milvis is completely open source, permissible license. So if you want to use Milvis and you want to put in your commercial product, you can do that totally free. We don't charge you. Okay, so in this talk, we're going to cover these 4 topics. Pretty simple. We're going to start with why RAG? Why even build something that is a retrieval augmented generation app? And then we're going to talk about chunking. So how should you chunk your data? How should you think about chunking your data? And we're going to talk about embedding models and some strategies around embeddings and how you can effectively use embeddings. And then we're going to finally, at the end, we're going to talk a little bit about vector databases. So the basic idea behind RAG is pretty simple. You want to use your data with a large language model. So how many people here have used an LLM? All right, that looks like most everybody. Okay, and you guys are all familiar with the term hallucinations? Yes. Okay, I see a lot of heads nodding. Okay, so hallucinations is kind of one of those examples that of one of the problems that we attempt to solve with this RAG type of framework, right? So hallucinations, an example of a hallucination is if you go to an LLM and you ask it like something it doesn't know the answer to, it's going to make something up. And so in order to kind of deal with this at an enterprise scale in real production, let's say you're working at a company and maybe you want to know how one of the products internal to your company works. What are you going to do? Read 6 hours of documentation? I hope not, right? Ideally, you can ingest that and you can put that into a vector database and you can chat with the documentation as if you're chatting with a person. And that's the point of RAG. So let's talk a little bit about RAG and fine tuning. So maybe this isn't as top of mind for people this year. I think a lot of people last year asked a lot about fine tuning. They asked a lot about RAG, but I've seen more people move into the RAG space and away from the fine tuning stuff, mostly recently. And I personally believe that is mainly because of the high cost of fine tuning with a minimal amount of results. So in terms of factual recall, so I'll cover what fine tuning is for in the next slide. So RAG looks like this. You have this kind of like very simplified architecture. you're going to take your data, you're going to put it into a vector database like Milvis, and then you're going to put an LLM on top of that. And then when it comes to query time, when it comes for you to ask questions, you're going to ask a question. The LLM is going to take your question, it's going to turn it into some sort of query, and it's going to ask the vector database for context. Once it gets the context, it sends that context back to the LLM, and the LLM says, okay, I'm going to turn this into something human readable. Here's the answer to your question. So RAG is really good for factual recall, basically, because what you can do is you can just give it all the context that it needs. It's also good for forced data injection and, as I was alluding to earlier, cost optimization. Not my alarm. Okay, so fine tuning is this kind of structure here. Basically, you're going to take your data, and instead of putting it into a vector database, you're going to skip that step, and you're not going to basically cache or hold the context to your data. You're just going to train your LLM on it. And then when it comes to query time, essentially you'll get a new LLM out of this. And when it comes to query time, you will query that new LLM. And one of the reasons why this doesn't work for factual recall very well is just the sheer magnitude of data and parameters involved with an LLM and probably the data that you have. So let's just think about this for a second. Does anyone have any idea how many parameters a small large language model might have? 1 billion? 7 billion? 7 billion is a pretty small large language model, right? We're seeing 130 billion, 70 billion, 200 billion. I mean, GPT-4 is like, I don't know, they haven't even released how big it is, but there's hundreds of billions of parameters that are involved, and the data that's trained on is like massive. I mean, it's called like the whole internet. And so the chances that you or your company has enough quality data to fine tune an LLM is very, very low. And because it has billions and billions of parameters, the training cost is going to be very, very high. So the main use case with this is, what you would want to do with this is give it the training data as if you were giving it some sort of context for the prompt. And so the way you can think about fine tuning is, it's almost as if you're giving it at the beginning of the prompt, you say, here's the style of data that I would like you to produce data in. So that's kind of fine tuning. And the takeaway from this is basically you should use RAG to force your LLM to work with your data by injecting it via a vector database like Milvis or Zillis. You can ask questions. So the reason why you put the LLM on top of the vector database prior to with the query, so you can do RAG in the way that you just mentioned. The reason why you put the LLM on top is because the LLM, you can use it to actually structure your query in a way that makes more sense. For example, if I ask the question, I don't know, like, what is a oh no, this is not a good example. How do I make beef stroganoff? Like, then what it's going to do is it's going to take this whole thing and it's going to say, okay, I'm going to think about this entire sentence of how do I make beef stroganoff. So then it can possibly find things that are similar. So vector databases work on vector embeddings, which allow you to do this thing called semantic similarity search, which I'll get into later on. But basically, you will find something that is more similar to the question of how do I make this, as opposed to maybe what you want is actually to find the recipe for beef stroganoff. And so the LLM can convert the how do I do this question into more a statement like recipe for beef stroganoff. And if you have that example in your vector database, it will return that to you. Cool. Okay, let's talk about chunking. Who knows what chunking is? Who's heard of this term before? Okay, you've heard this before. I've talked to you about this before. Okay, so you guys have heard this term before. So chunking is essentially taking your entire, like, let's say you have an entire block of text. Now what we're going to do is we're going to chunk it into readable blocks of text. So instead of an entire 42-page PDF file, maybe you have, 420 paragraphs, something like that. And so there's some considerations for this. So one is chunk size. How big do you want your chunks to be? Next is chunk overlap, which is how much context or how many characters should overlap between each of the chunks. And then the last one is this thing called character splitters. And these are these special characters that you may want to split your text on. And we'll cover why you would use these in this slide. So the main reason why we want to think about this, the way that we chunk our data, is because all data looks different. And the way your data looks is going to be is going to have a very big effect on the way that you should chunk it and interact with it. So for example, here we have some examples of conversation data, which is a bunch of like small, like, hey, how's it going? How are you? Blah, blah, blah. Like these like short little like texts. And then you have documentation data, right? So how many people here have read software documentation? Yeah? Yeah. Okay. So you know what software documentation looks like. It's not the same thing. You're going to want to chunk it up differently. The context is going to have to be different. And then finally, the third example I give is like lecture data. So let's say you're reading the transcript for some sort of MIT OpenCourseWare class or something. So these are all going to look kind of different, and you're going to want to have different chunk sizes and chunk overlaps and character splitters for each of them. So let's cover kind of what that might look like. So conversation data is something that maybe you want small character, small chunk sizes. You don't need a lot. You don't need a huge amount of characters. You just need to kind of get, one sentence at a time. And maybe you also want to throw that in there with some character splitters. Maybe you end each of the lines or each of the entries in your conversation data with some sort of special character. So that's one thing to consider with this. And you probably don't care much about like chunk overlap because you can get entirety context of like a piece of a conversation just without having to overlap from the sentence before. Of course, you can keep that, and we'll talk more about that in the embedding strategies. Next is documentation data. For documentation data, you're probably going to want bigger chunk sizes because you want to be able to get something that has something that makes that has a good amount of context in it. And you're probably going to want some overlap too, because you're also going to want to know like, okay, what was being talked about before? And maybe like what is this about to get into, and maybe how do we pull that data out, right? So documentation data, you're probably going to want to think about chunk sizes and chunk overlap a lot. And then with lecture QA data, see, you've got these like weird mix now. Now you've got some short sentences and you've got some long paragraphs. And so in this case, what you're going to want to do is you're going to want to think about how do I make it so that I can take a contextually sound piece of data and just work with that. And so in this case, what you're probably going to want to do is you're probably going to want to use character splitters to ensure that you are taking contextually sound pieces of data all at the same time. Your context size probably sort of matters. Your context overlap, not so much. What you're probably going to want to do to actually maintain context is to keep the questions and answers together, which is part of a metadata strategy that we'll talk about later. Yes. The chunking is trying to achieve what do you it's like, if you have 100-page PDF, for example, if you were to embed 100-page PDF, let's say 100,000, maybe 1 million characters, you're going to lose a lot of context in that because you're trying to stuff 1 million characters into, let's say, 768 dimensions, which is typical for a vector embedding. But instead, if you have, let's say, 500 characters at a time, then it makes much more sense, right? So it is essentially allowing you to get better access to the context in your documents. Does that make sense? Cool. Yes. I'm very glad you mentioned more tokens. Right. That's a really good. I'm really glad you brought that up because actually there's a lot of research that shows LLMs cannot handle much more than 2,000 tokens without losing middle context right now. Of course, maybe in the future that might change. It might grow. But there's a lot of research that shows like one of the big problems with passing in long chunks of text into LLMs is that they entirely lose context in the middle. I saw this YouTube video a while ago that was basically like, it was some guy who was just saying like, oh, LLMs suck. But really what he was showing is like, hey, if I pass the same 2048 character chunk into a bunch of these LLMs and I embed the sentence in the middle that says something like really, really out of context, I think I can't remember the exact examples, but I think his like original text was about like, I want to say he did the Paul Graham essay, and then he just added some random chunk in there, like about like something completely unrelated to Paul Graham, and he was just checking to see if these LLMs were able to check that was in there, and none of them were able to return that they had seen that basically. Okay, so now we're looking at this little slide here. That's just like an entire chunk of text, entire wall of text. I'm going to go to the next one so this makes more sense. Okay, so This is an example of, I'm going to show you, I'm going to walk through this example where I took a document on how to be promoted to each level of software engineering from junior engineer to distinguished engineer. And then I asked the question, and really, I asked the question something like, what does it take to be a distinguished engineer? And then I did a bunch of tests around the chunk size and strategies. And so in this one, we're looking at chunk sizes of 32 characters, and chunk overlap of 4. And I use character splitters on each of these, as you can tell, because they are different lengths of sentences. So this is the first one. If we have 32 characters and 4 overlap, and we ask the question, what does it take to be a distinguished engineer? We get completely nonsense responses. Okay, what if we go up? What if we go up to 64.8? So here we see that most of these responses are pretty much still like completely useless to us, but there's one here about Werner Vogels, who's the CTO of Amazon, is a distinguished engineer. So now we have an example of a distinguished engineer, but it's still not very good. What about the next one? So let's go to 128 and 16. So at this point, we see some more comments about what it actually takes to be a distinguished engineer. Has achieved noteworthy technical professional accomplishments while working as an engineer. And then we see the Werner Vogels things again, as well as provide solid technical leadership beyond the company and everything on the senior staff engineer list plus 15 to 20 years of experience. So this actually returns to us most of the data points on what it takes to be a distinguished engineer. So this is one chunking strategy that I would consider somewhat like pretty successful for this, right? 3 out of 4 is pretty. Okay, so now if we move up to 256, we see that where our responses, the text that we store and we get back is a little less readable, right? So who looks at this and it's like, I can read this? No one? Great, that's exactly what I thought. But okay, but now look at this and you're like, oh, I could probably read this, right? Who says they could probably read this? One person, great, that's better than 0. So that's 100% achievement, improvement right there. Okay, then now let's look at the next one, 512. So 512, at this point, these are just huge chunks of text, but what I want you to actually notice about this is that the first chunk that is returned actually includes all of the context from the 128 chunk, as well as the other piece of what it takes to be a distinguished engineer. And so the takeaway I want you to get from these examples that were just these huge blocks of text is basically your chunking strategy is not just going to depend on what your data looks like, as I alluded to in the beginning, but also what you need from it. Because you really could use the 512 and you really could use the 128. The main difference is, how do you want your user to interact with your responses? Do you want them to get pieces one at a time where they can continue to prompt for more and more information? Or do you want to give them an entire block at once where they may get all of the answers they need at once? So the idea is you need to think about how your users are going to use your information as well as what it looks like. Yes. Yes. So I did the chunk sizes and powers of 2 because, honestly, this is just what people have referred to as best practice. I don't have any real insight into whether multiples of 2 or powers of 2 are the only way you can go about it. My intuition is that you can really do whatever you want, but it's just easiest to show, like, it's easiest to kind of show the differences as you double up. Yes. So that is so that's kind of the idea behind character splitters, is to be able to split on specific characters so you have different size chunks. But what you've mentioned is it is possible. It is just annoying. Okay, good. Okay, so when we talk about embeddings, I'm going to give you another set of 3 things to think about with embeddings. One is, how do you pick an embedding model? 2 is, how do you pick what you should be embedding? And 3 is, what should you include as metadata? So first, let's look at some examples of where you can get embedding models. Okay, does anybody not recognize any of these icons? Everybody knows that icon over there, right? The yellow one. Everybody raise your hand if you recognize the yellow one. Yeah, okay, everybody knows Hugging Face. I love getting my free embedding models from Hugging Face. Okay, what about the second one? The second one in the middle, the one in the middle on the top? Okay. Really? You guys don't know OpenAI? Damn. Okay, that's great though. Okay, let's just pretend like you didn't hear that. Okay, what about this one? Who knows this one? You guys never heard of this one, right? Yeah, okay, that's because they're a super niche company out of New York, and they build these like really small large language models. But they're pretty cool. They build specialized language models for finance and law. Okay, what about this one down here? Who knows this one? Oh, just you. Wow. Okay, this guy here, right here, knows everything. So this is Anthropic. Who's heard of Anthropic? Yeah. Okay, more people have heard of Anthropic, and actually Anthropic talks about token size and how they have 100K tokens and stuff like that. So this is Anthropic. They've got Claude. I think Claude 2.1 is worse than Claude 2. What about this one? Who's seen this one? Yeah, you guys know this logo? Damn, for real? Y'all don't know PyTorch? Y'all don't know PyTorch? Come on, guys. You don't know the PyTorch logo? Dang. All right. Okay. What about this one out here? Who knows this one? All right. Llama 2, right? Okay. You guys know Llama 2. Okay. Cool. Okay. Just so you guys know, PyTorch is been around for quite a long time. They also have a lot of free embedding models on PyTorch Hub. That's actually where I get my image models. So if you want to play around with image stuff, I really suggest that. Okay. So let's talk about some embedding strategies, right? So I've kind of divided this up into 3 levels of embedding strategies. So level 1 is that you just embed the chunks directly. Just chunk up your data, embed the chunks, don't look at them, who cares? You're going to get the embeddings. This is fine. This is your basics, right? Level 2 is you're going to start thinking about, how do I want to embed these chunks? What do I really want to embed? And so in this case, an example of what you might do, and this is why I call them sub and super chunks, is maybe you have something like some text and it has a bunch of paragraphs in it. And what you could do to embed what I call sub chunks is you embed each sentence of the paragraph, but you attach that embedding to the entire paragraph. So why would you do that? You would do that if in the case that anybody searches for something that's similar to one of those sentences, you can return the entire context to them all at once. So that's why you do something like sub chunks. And then for super chunks, this is where you embed the context of, let's say you embed the entire paragraph and you link that embedding to just the sentence. So why would you do something like this? Essentially, what you would want to do with this is you want to say, I want to give specific responses to people who are looking for more generalized input. And then level 3 is really incorporating a bunch of metadata. So metadata is actually an incredibly important piece of your system, and knowing what metadata to include is quite important for you. So these are the 3 levels of chunking, and I'm going to give you some examples of metadata so you know what I'm talking about, because metadata is really this broad concept. So in chunking, some examples of metadata related chunking would be things like paragraph position. Where is this paragraph? What's the section header? What's the larger paragraph, right? So if we embed the sentence, what's the larger paragraph? What sentence number in the larger paragraph is your sentence? And things like that. So anything that's related to how you chunk your data is going to be a chunking type of metadata. And then there's non-chunking metadata. So there's things like the author or the publisher, or maybe the organization that wrote the thing. Or maybe you can even use this to do role-based access control. So non-chunking metadata is there for things that are not related to the way that you've chunked your data, and you want to store that with your vector embeddings. So the takeaway from this embedding strategy thing is basically your embedding strategy is going to depend on your accuracy, your cost, and your use case needs. So part of the reason why I showed you all these different embeddings models is because I'm pretty sure 4 of these are free. One of them, I'm not sure if Anthropic is free or not, but one of them is definitely not free. And that's the one that I was surprised that nobody recognized. All right, so now we're going to talk about vector databases. This is what you all came for. So first, we're going to talk about, oh, yes, sorry. We should talk after, but there are not a lot of those, and there should be, and I don't know why there's not actually. This is something that I've been looking at recently. I just wrote an article about the LLM stack. I was only able to find 3 companies that were really working on this kind of stuff. So, who knows? I think this is a problem space that a lot of people could be interested in solving. So that QR code there, I want you guys to scan that QR code. That's going to take you to the Milvis GitHub. Please give us a star on GitHub. I'm being told that that is very important to my boss. So so please do that. The basic idea behind vector databases, though, is that vector databases provide the ability to inject your data via this thing called semantic similarity. And when you're picking a vector database, the main three considerations you should have are, how much do you want to scale? Do you care about billion scale vectors, or maybe you only need a few hundred? And what is the performance trade-off that you're willing to make? Do you need something that's very fast? Do you need something that's very accurate? And how do you adjust that? And what is the flexibility? Do you need something that you can customize, or can you just kind of let the defaults be your guide? So these are some considerations, and we're going to talk more about them in a bit. So the first thing I want to introduce you to, as we alluded to earlier, is this concept of semantic similarity. And this slide is this graph is a very famous graph. And this graph shows that basically all you need to know from this slide is that vector embeddings let you do math on things that are not initially numbers. And the examples that I'm using here are queen, king, woman, and man. And I'm using two-dimensional embeddings, and I'm also going to use Manhattan distance. So 2 points here. If you ever see two-dimensional embeddings, get the hell out of there. If you ever see Manhattan distance, you're probably also in the wrong place. But it works really well for examples, okay? It really works well for illustration. So let's take a look at this, okay? So queen is 0.3, 0.9. King is 0.5, 0.7. Woman is 0.3, 0.4. And man is 0.5, 0.2. So I want you to notice here that woman and queen have the same value along this x dimension, this x-axis, 0.3, right? And king and man also have that same value. One thing I really want to make clear, that does not tell us what that dimension means. This dimension does not necessarily mean gender or sex, okay? All right, so this dimension is just saying that these words relate the same along this specific dimension. And that's all it is, okay? So let's look at this example. So queen minus woman, 0.3, 0.9 minus 0.3, 0.4. You arrive at 0, 0.5. Okay, this doesn't work well the last time, but let's try it again. Okay, who thinks they might know what 0, 0.5 might be? What word might you guess that is? Does anyone want to venture a guess? All right, nobody here is very brave today. Okay, well, that might mean something like, what is the difference between queen and woman, which might mean something like royal or regal or whatever, okay? And now let's say you add that to the word man, which is 0.5, 0.2, and what you'll arrive at is 0.5, 0.7, which also incidentally happens to be king. So like I said at the beginning, the only thing you need to really keep in mind from this slide is vector embeddings let you do math on things that are not originally numbers. So where do vectors come from? What the hell is a vector embedding? So you start with your knowledge base. You have some set of images, videos, text, audio, whatever it is that you are working with, and you have a deep learning model. And your deep learning model, this is very important as well, your deep learning model has to be a model that is trained on the type of data that you're embedding, okay? So do not try to embed images with a text model unless you're using a multimodal model, which I'm writing a blog about right now, so you'll see that soon. But the idea behind this is basically you get a deep learning model, you train it on some sort of data, and then when you're producing your vector embeddings, what you actually want to do is you want to cut off the last layer of the deep learning model. Why is that? It is because deep learning models are meant to do something called predictions. And we don't want a prediction. We want a semantic representation. We want a numerical representation. And that is the way that we can do math and compare these different vector and their vector embeddings, okay? And so then, you cut off the last layer, that's where you get your vector embedding, and then you store that into a vector database like Zillis or Milvus. And this is what storing data into a vector database looks like. I want to direct your attention to the first two rows. So one is ID and one is embedding. And these rows you have to have because you have to be able to look things up by ID and you have to be able to compare embeddings. Everything else is what I was talking about as metadata. The author, the publication date, who published it, how many times they clap for it, how long does it take to read, all this stuff, that's metadata, okay? So that's the basic idea behind a vector database. I think I'm running out of time, so I will try to cover this stuff really quickly and we won't get too deep into the architecture. So let's just briefly touch on why you would use a vector database or why these things even exist when you have SQL databases and NoSQL databases, because vectors are really just arrays. They're really just numbers. And you could store this in a SQL database, and you could store it in a NoSQL database. The reason why you wouldn't do that is because in order to compare vectors, you have to do a lot of math. Let's say vectors are hundreds of dimensions, and who here knows who here remembers like the distance between 2 points from geometry? X squared minus y squared, x1 minus x2 squared, okay, you guys get the idea, right? So that's like 4 calculations right there, and that's not even the most computationally expensive way to compare vectors. So vector embeddings are very computationally expensive, and NoSQL databases and SQL databases, these traditional databases, do not come with the infrastructure to easily do that. And so that's why these purpose-built vector databases like Zillis, like Milvus exist. Who here knows what a vector search library is? Great. I'm not going to say anything about this. Okay, Milvus, Zillis. Why Milvus? Why Zillis? What makes us special? We tend to play in the enterprise space. Our specialty is that we are a distributed database, and that we're able to handle horizontal scaling really well to enable you to scale to billions of vectors quite easily. Here's what Milvus architecture looks like. I don't have time to cover this. I'd love to talk about this later, but I don't want to cut into Damon's time. And what makes us different? So cloud native distributed system architecture. There's a true separation of concerns. So I'll touch on that in a second here. So as you guys can see here, there's a query node, a data node, and an index node. That's because these are 3 different things that you do when you are working with vectors. You want to be able to find where they are. That's query. Find the vectors. That's query. Ingest the vectors. That's data. And then create some way to access the vectors easily. That's indexing. And then we also have a scalable index creation strategy with 512 megabyte segments, which I will also talk about later if you would like. And the takeaway here is basically vector databases purpose-built to handle these index, storing, querying data, and Milvus and Zillis are specifically designed for high-performance billion-plus scale use cases. So if you want to start with a vector database and you want to scale into the billions and you don't want to have to do a data migration, who here has done data migration, by the way? Ah, yes, you understand the pain. Okay, well, the rest of you guys, hopefully you never run into that. So that's why you would use Milvus. And if you would like, you can join our Discord. And if you didn't give Milvus a star earlier, please go give Milvus a star. I will take 1 or 2 questions before I get out of here. Yes. When would you decide between fine tuning and rag? Like, you mean like, how would you decide? So, for example, if you want your app to be able to access data that the large language model wasn't trained on, so non-generalized data, maybe domain-specific data, that's when you would use rag. If you want your app to interact in a certain way, perhaps you want it to act like you would give it examples of how you act, and then that's how you would fine tune it, and basically it would essentially see that as like this is the way that I should be producing output data. Yes. Okay. Last question. I'm not sure I understand the question. Okay, yeah. Let's just talk about it afterwards. Okay. So yeah, thank you guys. That's my talk. I'm gonna let Damon come up now. He's gonna talk to you guys about how to use different vectors and compare them.
Great, thank you. Was anyone at my talk at this event, but at GitHub a week ago? I just want to know how much time I wasted redoing all of my slides from last week. That's good. Okay, cool. Well, it'll be new for you all then. I won't worry too much. So I'm going to talk to you a little bit about a project that's kind of a specific use case of a vector database that's kind of probably outside of the field of what you guys are normally thinking about. I'm a behavioral scientist by training, PhDs in psychology. I, basically use college kids as guinea pigs to do research and studies on. So pretty far afield from anyone that's doing like AI dev, engineering, etc. So the project I'm going to talk to you about is a multidisciplinary effort. It's a collaboration with my old advisor at University of Denver and some researchers from the Institute of Love and Time, as well as the Institute of Noetic Sciences. And what we are working, what our endeavor is here, is we're trying to create like an open source normative database of images. And I'll go through a little bit of detail what I mean by that. And the intention here is to use this as like evocative stimuli in experimental psychology research and applications. So when I say evocative, I mean either cognitively evocative or emotionally evocative. So these are basically like the types of stimuli that you'd use in various types of experiments, et cetera. Okay. So to kind of touch on the motivation and give a little bit of background and context, my dissertation research, a good bulk of it was around a technique, an emotion regulation technique called cognitive reappraisal. And let's say, for example, we show you this image in the lab and you see this like grueling negative accident. It probably induces some, negative emotions in the percipient. And the task then with cognitive reappraisal is to try to change the way you feel about this image by changing how you think. So you want to change or reframe the interpretation. You want to change the emotional meaning by thinking about the image in a different way. So this is a process of reevaluation or reinterpretation, reconsidering the emotions of the stimulus. And for example, you might say like, okay, yeah, that accident looks terrible, but you can see that the firemen are on the background there, so help has already arrived. You might tell yourself a story about the image, like perhaps it's not as bad as it initially seems. Maybe it's just a fabricated image to begin with. It's not even real, etc. So when we operationalize this in an experiment, then we will have conditions where we would show negative images and have the participant essentially just let their emotional process unfold naturally. They're not trying to intervene with their emotional state. And then they'll have them rate their negative affect, their negative emotion. Okay, so on some trials, you're just looking, letting the emotion unfold naturally. Other trials, as like kind of a control baseline, will show a neutrally valenced image. And so you can see like, okay, if things are working properly, you'll want to see a pretty large differential. This is really reflecting that this is not a negative image, and this high rating of negative affect is, pertinent to the negative image and not the neutral image. But then we have these other trials where we're asking the participant to change how they feel using reappraisal. And what we're really interested in then is this differential between the look and the change condition, which we'll basically call reappraisal success. So on average, are people able to reduce their negative affect when they're trying to change how they feel? Does this make sense? Yeah. So yeah, no, that's a good question. On each, these are averages over like number of trials. So if participant A, let's say, saw this injured person on a look trial, they will not see it on a reappraised trial, because then you kind of confound it with order effects, et cetera. So this is the important thing here, is that this is not really at the trial level. This is at the aggregate level. We're going to average trials across these different conditions and look at that reappraisal success as like kind of the average differential. Okay. So a lot of these images are often sourced from normative databases such as the International Affective Picture System. This is kind of leveraged, and there's similar databases as well. These are leveraged across various, behavioral research, et cetera. And the key thing about these IAPs is that they contain numerous images that vary in their affective quality. Okay, so we have this image of the snarling dog, for example. And when I say normative, what I mean is that they've fed these images to like literally thousands of raters to get subjective ratings, and in this case, valence and arousal. When we think about valence, we think about the kind of the positive to negative gradient, and arousal is like the emotional intensity. So let's say hypothetically this image of the snarling dog is relatively arousing and relatively negative. And so we can kind of plot that almost on a two-dimensional plane. Make sense? The problem is that while this is really useful in helping us to kind of derive what stimuli we want to, anticipate is going to evoke a negative response in the participant, this type of rating scale doesn't tell us a lot about the meaning of the image. Okay. So for example, if we take this snarling dog, it really evokes a sense of a close physical proximity. It contains an immediate visceral threat. It's a concrete or non-symbolic representation. So what I mean is all of the emotional information, you could argue, is already contained within the image itself, right? You don't have to make a lot of inference here. Another way of saying that is that the emotional meaning is derived from the bottom up. It's like sensory driven, right? So you're experiencing arousal from looking at this image. That arousal is really indicating that you should move your body and run away from the dog. Let's contrast that with another negative image. And let's say hypothetically that these are relatively matched on that arousal and valence scale, okay? But in this case, it's quite different because there's this temporal gradient, this temporal distance. There's no suggestion of an immediate physical threat from this image. This is something that happened long ago, for example. It's also quite abstract or more of a symbolic representation. It's more like the archetype of a Nazi, not necessarily this specific Nazi that's important here. And so any arousal that you experience is kind of removed from the present threat of physical harm. And you could also argue that the emotional meaning is non-sensory. It has to be derived from the top down. It's more of a cognitive process. To understand that this Nazi is negative, you have to have all of this other contextual information about World War II and history, etc. Otherwise, it's just a guy really in a brown suit with an interesting symbol on his sleeve. Doesn't mean anything in and of itself without that context. Does that make sense? So when we think about this in terms of reappraisal, we can think of this Nazi as being embedded in a much wider semantic network of inference and meanings. And some of those are positively connotated, like, concentration camps and Hitler and Nazi propaganda. And some are a little bit more positively context, right? Like, so you can think about the Allies winning the war or the formation of the United Nations, etc. And all of these might be kind of threads that we could pull on the process of trying to change how we think about that image. And we could also argue that reappraisal as a technique is a very top-down strategy. It's requiring a cognitive process to really engage with, to come up with other reinterpretations or reframings. So I want to take a step back and talk about another formative theory, which is construal level theory. Construal level theory argues that psychological distance is a key factor that drives our mental representations, and that these mental representations will fluctuate between proximal, like here and now, or direct sensory experience, to distal, things that are more removed in time or space, or even actuality, if it's more hypothetical or actual and literal. And so the idea is that as things become more removed in space or time, we tend to use more of an abstract handle for thinking and considering it. And I'll give some more examples in a moment. So this is great for us because this is allowing us to form these more mental construals that are abstract, that kind of represent distant places, times, other social conspecifics, etc. And this really allows us to kind of manage our mental simulations, right? So you can do a lot of planning and forethought by simulating these, kind of more abstract futures, etc. And so this really helps facilitate thinking about the future, remembering the past, imagining counterfactuals like what could have happened, etc. Oops. Yeah, so as I said, this kind of increasing psychological distance across any dimension tends to trigger more abstract mental construals. And so the further something is away in time or space, we tend to think of it more as a general idea, the gist, like what are the essential features of the situation. And importantly, we tend to focus on why versus how when we think about things in the future, for example. Let me give you an example. So when you thought about coming to this talk tonight, you might have thought about previous talks that you've enjoyed at this venue. You might have thought about that there's free pizza. You might feel generally connected to like AI Camp, or you might have thought that maybe Yujian would be handing out free socks again, which he didn't. So this slide's kind of moot, right? So there's a lot of reasons why. But when you're actually in the day of, like this afternoon, then you really have to kind of construe the problem as how, right? You have to reorganize your schedule. You have to think about the traffic on the bridge and which route you're going to take. If you're coming from Seattle, for example, what's the route you're going to take? So it's it's a different problem space than it was a week ago when you got the invite. Does this make sense to everyone? So when we think about construals of these kind of like, I'm going to use this kind of cone metaphor, and we think of these as different types of construals that are broadening across this vector of psychological distance. Whereas, let's give an example. If I have like my specific phone that's in my pocket at a low level of representation, I can think of it in a way that maybe has a crack on the screen, it has like an orange case, etc. It's very idiosyncratic and specific. But if I pull away from that, it's really just an iPhone, right? And thus it's kind of semantically related to other types of iPhones. And in that respect, it's actually related to mobile devices more generally. Or we might pull back a little further and say it's really just a phone, right? And if we pull back further still, we can say it's really just a device for communication. As such, it's somewhat similar to things like the fax machine or even the telegram. So when we look at the example from the previous talk of like king, queen, and man, woman, the problem with that model, and I think maybe what Yujian would agree, is that it's treating those distances as fixed entities, like the semantic distance is fixed. And where I think you can really exploit more modern models is using more of a flexible, dynamic definition of context to define what that semantic distance should be. Does that make sense? If we treat semantic distance as a fixed entity, we're going to run into problems because it's really contextually driven. Yes. Yeah. Well, so like we'll probably go back to that offline, but yeah. Okay. So let's take this kind of semantic network example. And if we think about like the gramophone versus the iPhone, that should have a really pretty far away semantic distance, right? Those in vectorized space, those should probably be pretty disparate concepts from each other. Yet when you activate the concept of music player, the relative distance of those contents should be shorter. Does that make sense? Because now it's within that broader context of music player, those things are more related to each other than they would otherwise be. The example I like to give is like dogs and airplanes are pretty far apart from each other semantically. But if you have to travel with your dog and you're flying to another state, you got to think about which airline will take dogs, which is Alaska, by the way, right? Dogs and airplanes becomes a lot closer semantic distance in my problem space. Does this make sense? Okay. So the important takeaway here then is beyond the contents of an image, it's really the manner of depiction that really influences that mental representation. So it's not, the emotion really is not being by virtue of it being a dog, because here you have a very positive valence dog. It's not by virtue of being a Nazi, because now you have a cartoon example of a Nazi, which probably doesn't induce that same level of negative affect. Does that make sense? So it's not necessarily the what, it's kind of the how that really drives that experience and the mental space that the person considers it in. Okay, so the other problem is like if I use kind of, let's say, state-of-the-art tools as of circa 2 years ago, if I'm going to use like Google Vision to classify images, it does a great job of telling me what's in the image, but it doesn't really capture what it means, right? It can tell you the objects that are in the scene, but not much information about how the person's going to react with that image. So let's get now into the present design. So that's kind of the background, and I'll talk about the actual project that we're working on here. So we are gathering, right now we've got a small database. For me, it's huge because I'm from experimental research and we deal with small scale stuff, but for most databases, it's tiny. We only have 2,500 images, but these are gathered from various sources, free photography sites, sites, etc. And for each image, we've defined 18 classes. And these are kind of separate psychological dimensions that we think are important for kind of encapsulating the meaning space that the image is embedded in. We are running a large-scale study with human raters that are, derived from the University of Denver, volunteers, as well as Amazon Mechanical Turk workers, and we're having them rate each image across all of these 18 dimensions. And so this amounts to over 2,000 participants so far and over 760,000 unique ratings. And so now for every image and for every class, we have this kind of normative distribution. We have not just the average and the standard deviation, but you have the whole distribution of ratings for every class, for every image. And so these classes were informed by construal level theory as well as other previous lines of psychological research. Okay, so here's just a preview of some of the classes that we're collecting. I won't go through all of these, but we're looking at things like the level of abstractness that the image evokes. If it's sensory, like does it tend to evoke a sense that you're experiencing it in your body, for example? Is it visually simple or complex? Does it evoke a sense of temporal distance? Like does it feel like it's removed in time in the future or the past versus feeling closer to the present moment, et cetera? And here's an example of a question that a participant will see. So animacy is one of the items, and you'll have a kind of a paragraph description of what the question's really asking to make sure they understand what they're being asked. And the participant will kind of move the slider to either inanimate or very alive. We'll have anchor points for every question. And those anchors then are translated. So the slider values are translated from a 0 to 100 scale. So in this case, animacy, very alive would be 100 and inanimate would be 0. Make sense? Okay, so now instead of just having, let's say, object classes for an image, we now have these kind of database norms that give a little bit more information about the meaning space, like the level of abstractness or if it's interesting or not, et cetera. The next step is to port all of this over into a vector database. And so the first step I've done with that, and it's kind of following on with Yujian said with Hugging Face, I'm using a efficient net B4 model and pulling that last invisible layer and capturing the visual embeddings from that model. And so, those embeddings capture some of the semantic information, but also the general composition of the image as well. Okay. From there, calculating the cosine distances for every image pair in the database. So you can see like kind of the relative visual distance between the two. So you can kind of see like what images are more visually similar to others, et cetera. To get the more semantic information, I've run the images through a multimodal model called Lava. Has anyone here used Lava before? Yeah, cool. So you can ask, it's like a LLM interface to talk with your images. So you can ask any kind of question you want about the images. I just asked to provide a general description with like 256 tokens. So we get a kind of a paragraph caption for every image. Here's an example of a description. I won't read it, but it's an example of a description of this cemetery image. It does a really good job of kind of describing the main features of the image and like kind of the meanings about the image. So from there, running the semantic embeddings through, running the caption text through OpenAI using a text embedding ADA2 model to get the vectors or the embedding vectors. So basically take the caption text through the embeddings model on OpenAI, and now you have this kind of text as vector, which is very much like the last talk we talked about. Okay, so just like with the visual information, now we have the semantic similarity, and we can use that as like kind of the 1 minus the distance is giving you the similarity. And this is kind of an idea of what that looks like. So every image compared to itself and compared to every other image in the database. So just as a example of how this is working, so I have this reference image, which is the cemetery. And when I find a close semantic match based on the captions, It does a really good job. So this is the closest image in the database. It's picking up on the fact that it's a cemetery. So far, so good, right? And here's the closest visual match, which I think is interesting because it's picking up on the field and the trees. And notice the uprights, which are kind of similar to the gravestone uprights, but not semantically similar. They're fence posts. They're not graves. Make sense? So both of these could be useful in different contexts. So next steps, we want to transition this from MATLAB, where it's currently sitting, into a true vector database, probably Milvus and Zillus. So, capturing both those visual and semantic embedding information. And then I also want to take a step and try to compare the results of the captioning with other multimodal models, such as CogVLM or ChatGPT-4v. And the rating info and the distribution characteristics would be added to the database as metadata tags. And so ideally what this would facilitate is a keyword search and reverse image lookup. So you could feed a new image, caption that image, get the visual embeddings, and then find the closest exemplars in our database in case you wanted to find like similar match stimuli, et cetera. Ultimately, the goal is to create like an easily searchable open source stimulus repository that facilitates future research. So I want to give an example of a specific use case. How am I doing on time? Okay, good. Yeah. So this is kind of going back to the research context, how we'll be using this. So I mentioned, a typical cognitive reappraisal study. We're really interested in this kind of averaged distribution or averaged aggregated under these different trial conditions, and that reappraisal success is that differential between look and reappraise. My dissertation work, I took 27 different reappraisal studies and kind of aggregated them. And this was 150,000 different trials and these look and reappraise conditions, had over 1,435 participants and 454 images. So these are not the same images in the image database. These are images that were from that earlier IAPS databases that are really negatively valenced, gruesome, and some of them are like severed limbs and kind of nasty and stuff like that. So why do that? So what's interesting about having that database project as my dissertation is now for any image in the database, I have the distribution under different conditions, right? So I have this image of the soldier pointing the gun at the kid that's running, and I have the ratings when the participants are looking and letting their emotions unfold naturally, or when they're trying to change their experience through reappraisal. And what this gives us then is this kind of image by image reappraisability metric, which is that mean shift. Like when people are reappraising, that they are rating on average as being a little less negative than when they let their emotions unfold naturally. Does that make sense? And so beyond the image valence and the arousal, what we want to know is what predicts that? What allows you to change the way you feel about these images? And interestingly, I showed this image before. This is actually an example of our database that's an unsuccessful reappraisal example. What I mean by that is like when people try to reappraise this image, on average, they're about 0.31 standardized units more negative than when they just were sitting there letting their emotions unfold naturally. It's like totally a paradoxical effect. But you think about like, why would that possibly be? Well, you see, let's imagine that you kind of like take this into an ecological context. If you come across like a snarling Doberman that's got a spiked collar and looking that it wants to bite you, should you be there like, how do I feel better about this right now? No, you should probably run away, right? And so there might be a kind of ecological fit that's really going on here that's kind of explaining that issue. So one way of thinking about this is this idea of affordances. Affordances is a term that was coined by Gibson in '79, and it really describes like the form of objects that surround us that shape our perceptions about what we can do with them. And so the canonical example is like the handle of a suitcase affords it being carried. Does that make sense? And so when we think about, this is just a side example. There's this artist that does these objects that have like, they've taken the affordances out of it, right? So like the fork with the chain handle, like there's no affordance now, right? Or the pitcher that pours into itself, or the rain boots with no toes. So this is just kind of a play on that. But when we think about reappraisal affordances, then, is this opportunities for semantic reinterpretation that are inherent within the image. So kind of going back to this model here, we can think of the dog as existing in this like maybe low level of representation with a smaller network of semantic associations that might offer fewer affordances for reappraisal. Okay. Whereas the Nazi is embedded in a much broader semantic network and perhaps offers more affordances. Is this kind of clear to everyone so far? If you're interested in this work, I'll just leave this up here for a second. But these are the two papers that kind of deal with this issue that I'm author on. So what we're trying to do then is a pre-registered study. I've been collecting the same ratings that we're doing for the image database, that we're doing the vector database, on these gruesome images that we use in the lab. And the first question is like, what combination of class components, those 18 classes, might predict what the affordances are? Basically, can we describe affordances in like some kind of component model of those 18 classes? Secondly, does the visual or semantic similarity relate to the similarity in reappraisability? So if I look at every image and how reappraisable it is in terms of those mean shifts, is that predicted by the similarity of the semantics or the visual space that the images are in? Does this kind of make sense? So we're trying to basically unpack like what renders an image a little bit more malleable to our cognitive reappraisal process. Yeah, so we have the kind of the classes that we'll try to use as the predictors of reappraisability. Okay. I think I'll just open it up for questions. This is my LinkedIn page. I'm happy to connect with anyone if you have further questions about this stuff or looking to collaborate on mad science type research. But otherwise, thank you. Yeah. Yeah. So the question is like, basically, how are we using the radars to get to the different images? So depending on the version of the task, any radar is only going to see a subset of those images. And then we broke those. Go back here. We broke those classes into 3 groups. So we have basically 3 versions of the experiment. Here we go. So order 1, order 2, order 3. So you're randomly assigned to one of those orders. So you're only getting 6 questions per image. And this was done intentionally so that you're not getting embodiment and sensory, which have like kind of overlapping concepts in the same, with the same radar. But yeah, to answer your question, ideally we want kind of a distribution of ratings. Because when we look at even like negative images, we can't predict any individual's response to a negative image. But we can say on average, this image will evoke a negative emotion. Does this make sense? So on average, this image might be interpreted as more abstract, et cetera. And it has been interesting because some of these, depending on the image, have like really wonky distribution characteristics. Some are like more bimodal and some are way more normal. So this is something else that we're investigating. And this is stuff I talked about last week as well. Any other questions? Yeah. Absolutely. Yeah. Yeah. So of course, every rater is going to respond and interact with these individual images in a different way. And there again, that's why we want to get distributions of ratings, not individual ratings, right? Because some when we look at like temporal distance, like it's one example is an image in our database. It's like a young woman wearing old timey clothes, and some people see it as like a recent image, and some people see it as like an old image, right? So we don't. By having a lot of different ratings that are kind of clustered around that, we can say like, what is kind of the average for the population as opposed to like any one, individual. Make sense? Yeah, Michelle? Yeah, well, so interestingly, I'm talking specifically about the lab applications for this, but cognitive reappraisal is a big part of, has anyone heard of CBT or, cognitive behavioral therapy? That's a large component of cognitive behavioral therapy. So there's a lot of clinical applications for this. I've been more on the experimentalist side as opposed to like the clinical side, but absolutely. I mean, I think there's a lot of applications and implications for this. And you can even in like more industry setting, like advertising and marketing, right? You think about branding, sometimes it behooves you as a brand to appeal to like a higher level of construal, right? Or if you want more of like brand recognition, but if you want more action, right, it's better to appeal to a lower level of construal. Like if you want your customer to really interact with your product in a very specific way, you might want to target it in more towards a lower level of construal, if that makes sense. Okay. I don't want to take any more of the next speaker's time. So yeah, thank you again. And I'll be around if you want to ask questions after.
Thank you very much, Damon. Our next speaker is going to talk about stream processing, specifically real-time stream processing, and she's from a company called Bytewax, and she's dressed as a bee. And we're really glad that she's here. She's our keynote speaker. She's wrapping up.
Yeah, I'm going to talk about the built-in RAG application, but was a real-time streaming pipeline. And actually, I was worried before coming here that I wouldn't have enough time to cover everything I wanted. But Yujian thankfully had exact same points on chunking and overall about the vectors. So I'm going to skip a lot of theory and hopefully we have time. I even might end up being shorter than I wanted. But anyway, and also this is the first time I'm using this software, Snapify. It looks fancy, but if it doesn't work, I warned you. Yeah. So stream process embed repeat. Yeah, this is nasty. Stale brat. If you serve that to your clients, they are not gonna come back to your restaurant. Same with data. If you serve stale data, nobody's interested. Here's some statistics from LinkedIn. That's how the delay between recommendation of the job, the posting, and how delay affects actually the number of how many people click on it and try to submit their application for the job. So as you can see, if it's within minutes of how you posted it, everyone is clicking, and that's kind of the baseline. And then the further you go, if you run this recommendation job once in a day, then you're going to lose almost 5%. That's a lot. And you can think of many examples how that could be bad. I just thought that it's nice that they posted this little case study and shared this data with us. So let me introduce myself. I'm Oli. I work for Bytewax. And like Yujian said before, his company, they like when you go and start their repo. We do like that too. So if you go to github/bytewax/bytewax and give us a start, that would be awesome. So I'm a proud human and dog mom, and I'm expecting my second one soon. So this is my daughter, Aurora. And we're hiring at the moment. And if you're interested in DevRel or developer advocacy, this is my team at a current conference. So check out this QR code and you can apply for developer advocate. So today's agenda, well, we'll skip the entire part probably about RAG and embeddings and jump more into the technical implementation of my pipeline and then look at the code. I was going to talk about like how you can approach the staleness of your data, blah, 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 but Eugene covered it all. I'm happy. No need to say anything. And then he also talked about how you could, in theory, implement the RAG. And here, well, I have to stop because I'm wearing Stripe striped yellow shirt. So, and usually a lot of people actually use this king, woman, man, queen, blah, blah, blah example. And here I just like that it sounds a little different, but the idea is the same. So if I had a striped yellow shirt made from cotton, maybe it would be like bee themed shirt, something. Anyway, so today I'm going to actually talk about the part where you ingest data, your canonical answers, or something specific to your domain or your company that you have into this vector DB. And you're not going to guess which vector DB I'm going to use. Yeah. So this is the yeah. So our source is going to be Hacker News, and I believe a lot of people use it. They post their comments, or like the general idea is that you share your link, everyone upvotes it. And again, if you care about stars, that's probably one of the best sources to get stars to your repo. If you post it on Hacker News and it's hyped, it's on the front page. Yes, you probably on trending repos, and you're gonna go through your investments round. Cool. So Hacker News has a public API. It's interesting. So they allow you to poll for the max ID, the maximum ID of the story or comment they have there, and then you can send the request again and say, hey, share some metadata or share the content. If it's a comment, then it's text. If it's a link, then it's a text in the link, and then they have polls and something else I don't remember, but it doesn't matter. So it's publicly available. And we're going to convert this into we're going to convert this into a real-time streaming data source. So if you used Kafka, then you know that there is a consumer, there is a producer, and actually it's not the producer that pushes information into consumer. It's consumer which polls constantly every so often producer and say, hey, give me more data. So we're going to do the same. We're going to just start the pipeline where we're going to send requests to this Hacker News API every 15 seconds and then work from there. So in order to do that, we're going to use ByteWax. ByteWax is an open source stream processor in Python. So it's Python native API, and you can check nice talk by our CEO, Zander, where he talks about the origin and why ByteWax exists in the first place. So he and some of the founding members of ByteWax used to work at GitHub, and he was a data scientist there. He was responsible actually for pipeline that serves this trending repos. And yeah, that would be nice if we were ever on this trending. But unfortunately, even with insights he has, we not necessarily get there very often. Anyway, so the problem there was that there were a bunch of data scientists who were not necessarily very familiar or had enough expertise in JVM. But a lot of solutions like Apache Flink would require you to run JVM heavy, monstrous, if you will, application, and they wanted something similar, and that's how the ByteWax, basically the idea, they had this idea, and it's built on top of the performant Rust engine, which is a timely data flow, and because of the bindings, projects like Maturian and Pio3, you can just rub that, and the end user of ByteWax will never actually have to deal with anything Rust related or JVM at all. We don't have it. So anyway, we have many ways to connect to input sources and output sources. I'm not going to make you guess guess this project based on their logos, but I'm sure you know a thing or two. And here's the pipeline. So I'm going to use the Hacker News, and then we'll do processing step by step using Unstructured and Hugging Face, and then write the results, the embeddings into Milvus. So here, the interesting part is probably that everything is in Python, and we can leverage the entire ecosystem without actually having to do anything else except for the Python. And also for Milvus, I used Milvus Lite, which is in-memory version of Milvus, and yeah, I have a GitHub repo. I'll be sharing the link at the end so that you can go and check if you're interested. So let's start with the Hacker News API. And here's the pipeline. So at ByteWax, we're building a DAG. So we're like, and we start that, we call it data flow. So data flow is an abstraction, and you have different nodes on it where you can do different operations. So in order to start node, you just write data flow, its name, and then import, of course, ByteWax. So here, I'm trying to connect to start to initiate this data flow with the input source. So I wrote a little class here, which is basically the simple polling source, and I gave it the URL to poll, and we're gonna poll it every 15 seconds. So that's gonna be our input. So here is just like Hacker News API URL. So, but then after we got all this max ID of the source or whatever, we need to do something with it, right? We're not gonna write IDs to the Milvus database. It doesn't make sense. So the first thing is to actually, so we're gonna get a bunch of IDs at the same time, and here in this step we try to read them, that flat map, and redistribute. So I'm gonna go step by step to explain what every step means. First is this stateful map. So here we get the max ID from that request, and then ByteWax captures the state, so it knows what the previous max ID was, and it tries to generate using get ID stream. We try to generate the IDs between the previous max ID that we had and this new max ID that we just got. So, and for the very first initial step, we're gonna just look at the last 150 items. So, and ByteWax saves this max ID along the way for the pipeline, and then so we now have, for each max ID, we have a list of the key IDs. So now we're flattening it so that we just have a pipeline of IDs, and they're just going. So then we redistribute, because you can run as many workers for ByteWax and throughout your cluster as you want. I'm not going to talk a lot about this right now, but the idea is that you need some scaling, and like usually it's like your Kubernetes cluster or whatnot, and ByteWax natively is cloud native, so it's easy to do with ByteWax. So once we have this IDs in our ID stream, we're gonna download the metadata. So the metadata would contain different information, including like who wrote the post, when did they do that. If it was a comment, then we're going to have the parent ID of the story they commented on or a previous comment. And so in order to do that, we're going to use the filter map. And the filter map is just basically for each ID in this ID stream, I'm going to run this download metadata function. And if it returns none, then we're going to omit it and not going to send this downstream. Sometimes it happens because the internet, right? And we send a request and try to see what the JSON has. So if it's none, then we say, hey, I don't know what happened, whatever, skip it. Then we're going to check if it's story or comment, because that's what's interesting for us for this particular example, and that it's not dead, because sometimes they ban it and then it's not clickable, doesn't have any valuable information that we could put into the vector, convert into embedding and put it as vector DB, so we're not going to use it, and things like that. So we're just basically preparing some data based on the metadata. But then for this example, I want to branch out and split our stream into two. If it's a story, then I want to be able to go and check the URL that they posted with the story and actually retrieve some data from that URL, process it, and save as embedding. For the comment, I want to go back in recursive full tree to see the context for that comment and also build an embedding based on it. So yeah, here it's just simple. You give this a stream and then you give a predicate, and it's going to split based on true, false. So say we have stories. Yeah, the question here was like, what's the document type? If it's a story, then we're going to save the stories into this variable here. And now we're going to download the HTML for this stories, which is pretty simple. I'm going to skip it here because it just requires get blah, 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 JSON, whatever. But the next part is actually interesting because Yujian just talked about like chunking data. And when you had this, when you download the entire HTML, it could be like super big or not informative, or like you need to actually pre-process it before building embeddings based on it. So we're going to use unstructured on it. And I really like that because Bytewax has Python API, like you can leverage whatever library you have in Python, and you have libraries for everything, including this. So yeah, once you got the HTML for stories, you're going to parse the HTML. And the idea is that you Unstructured can kind of tag your content and help you decide which parts are meaningful for you based on this text, help you retrieve, like parse the parts that we're interested. So I'm interested in this case in the narrative text that I want that's what I want to save to as embedding to my vector DB. So here's like basically some cleaning happening, and after which we'll do the chunk part, and smart people already told you how to do that. So yeah, that's cool. Do some cleaning off. Basically now you have a piece that you can, yeah. Unstructured. Yeah, so this one it has to do with the unstructured that I used. So there are keywords there that I think there are like content or something like that, maybe. Yeah. So, well, I think you can do content specific, but this one is not. I think you can give like yeah, something that you're interested in. Yeah. Anyway, so once you parse the docs, now you can actually create embeddings based on it. Yeah, so here I'm gonna use Hugging Face because yes, free, open source, cool. Yeah, and for that, basically, not gonna go into details again because time, but you just give the document, the tokenizer, the model, and PyTorch, whatever, then dimensions, and you get the embeddings actually. And the interesting part here is how to save the data back into the vector database. Because remember, it's streaming, it's constant, the data is constantly coming. It's not like you wrote it once or preloaded all your documents and forgot about that. No, the data is coming. We're actually getting new information from Hacker News all the time. So we can ask questions like, what's up, what's hot there? And well, if we connect this vector database to LLM and blah, 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 the other side of the pipeline. So first thing is that when you're building input connectors for stream processors, it's usually that you tell the stream processor how to initiate what to do first, and then what to do when the new chunk of data is coming. And it's true for many of them, it's not specific to ByteWax. So here I'm just for Milvus, and I use PyMilvus, and I use Milvus slide. It's very simple to set up and run the server, so I skipped that part. But here, basically, for the host and the port, I initiate the connection, and then I try to see if this database already has this collection. And here I decided that I want to drop it and create a new one. And then in build, actually, so after I know what to do in initial stage, so I connected to it. In build now, we can talk a little bit about what to do when it happens. Again, in initial start, then write batch is an interesting part. So here, first we already have these documents as embeddings and everything. So we just insert them and flush. And here, unfortunately, I didn't know that before, but Yujian nicely told me just before this meetup that actually I don't have to create index on each insert, that Milvus automatically creates it after 15 megabytes or something. So I could as well skip this part with index, but still it almost doesn't hurt at this level that I do that on each step. So yeah, that's the simple parts of everything. I want to kind of go back to the diagram. So we had our Hacker News API. We converted it into streaming by doing the poll every 15 seconds. Then we cleaned up it from like dead or irrelevant comments and stories, etc. Then we downloaded the HTML and tried to retrieve the narrative text from these HTMLs. There is another part which I don't show here, but if we have time, I'll go and we'll see in my IDE where we go through recurse through the comment tree. Then for each of these, we calculate the embedding, and then we just save this in vector database, and it's ready to use for whoever uses it for RAG. Okay, so yeah, demo time. A little disclaimer. I wrote this on my Mac Mini, which has M1. And this one, so the Mini is Apple Silicon, and this one is Intel-based MacBook. So fingers crossed it works. Yeah, well, already something happened. We just do this. Whatever. Yeah. Well, let me. Why is it so small? View. How do I visit appearance? Zoom in. Okay. Sorry. Yeah. Module not found. What? 1 second. No, I ran it on this laptop, but just once. Let me see what's going on. How did I do it? Let's see what's there. Just kill it. Well, in theory, it's not. It's probably not connected. Because I'm trying to read from in real time. Yeah.
Oh, you have your phone connected. Okay.
No, my phone doesn't actually. Yeah, I don't know why.
It's up to you guys.
This one.
Yeah. Pop up with like an event code. Go to like Google, see if it works.
I don't think it works. No.
Maybe like disconnect and reconnect. It should pop up with like a screen.
It didn't for some reason. Like the first time I clicked on it, it didn't. Yeah.
Let's go like sign in.
Yeah, that's a little bit risky to do the actual demo with. Yeah, it can't connect to the internet. Well, let me try my phone again. Where did I put my phone? It work now? Well, the idea was that I would run it and then connect from Milvus CLI to do some queries, and we could see in log the data that is coming through and how the it goes through each step. But I guess without internet we cannot do that. Well, you just Oh, okay. Yeah. Well, it's from my phone now. I don't know. Is it gonna work now? Might not still work. I don't know. Well, it works. Let me see. It doesn't hear. Why? Anyway, while we have this hiccup, You can go to the GitHub Bytewax and real-time Milvus. That's where, or scan this QR code. Where is it? At the very end. Yeah. Scan this QR code for the repo. So the entire code is there and the instruction how to install everything and get it running. So it was really nice to have the Milvus Lite because it's embedded and you don't have to deal with the Docker Compose, blah blah blah, standalone running. At least for the demo for like trying something, it's really cool. So I just wanted to add that Bytewax is, you can actually think about tons of different real-time or not necessarily real-time inputs that you could connect, WebSockets, Kafka, Red Panda, like you name it, and then run the your regular Python code with it. So let me see one more time. No, why? Maybe I didn't connect. Didn't download the. Well, maybe something is happening with VS Code. It can't even fetch origin. Does it say? Unable, yeah. Whatever. Okay. I guess we're gonna go without this. Yeah. Yeah.
About the distributed.
Yeah.
So when Bytewax or kind of your Bytewax like PAG, the kind of script that you write is running in a distributed environment, is that like just being written, the script being replicated across the different I guess environments?
Well, it depends. It depends on like how you run it. I ran the just the local-ish version. It just ran multiple workers, meaning processes and threads, not necessarily like across cluster, but we have a bunch of tools and like including VaxCTL, which is like Kubernetes help to work with Kubernetes. We also have so Bytewax is the open source project, but we have a platform where you can monitor and like do observability for your pipelines and also see how it goes within your cluster. It's okay. No, thank you. I'm fine. I'm already gave up on it. Yeah. The feature parity was Flink. So like Flink is huge for the majority of things, like window and aggregation and like filtering, some stateful operations where pretty much have the like production ready core. But for many different things, of course, Flink would be ahead of us, especially customized connectors. Like here, I wrote a very basic one for Milvus, like it's output connector. But actually, there are a lot of things to think about when you think about like recovery, because Bytewax does support disaster recovery. So when you stop somewhere, you can basically go to the checkpoint that you have and like we save the state, and then you can recover to it. But then you have to have connectors to your input sources and output things that would support that too. And of course, Flink would be much more ahead, but that's also a very established product. And Bytewax is, we do have customers who has it in production, but differences there. I'm not going to tell you like it's. Yeah. Thank you.
Cool. Thank you for that talk, Ollie. And thank you guys all for coming and being here. These events, are entirely reliant on people being interested in coming to them. Otherwise, I would not be hosting these. So thank you guys all for being here. If you would like to support me continuing to do these a little bit more, I'd love for you to come and talk to me about, assuming this thing connects to the... Well, damn. All right. Well, if you are interested, here we go. Okay, cool. Okay. So, if you are interested in, continuing to support these events, I would love to know a little bit about, come talk to me. Come write a little bit about how was the event? What did you learn? What was your favorite thing? I'd love to get you to do like a short video interview, or if you just want to write a little post on LinkedIn or anything and tag me, I'd love to know. And then I'm going to advertise my hackathon calendar again. So lu.ma, lu.ma. It is not a Chinese name. It is just some site called Luma. And the calendar is called OSS for AI, Open Source Software for AI. I'm a big open source enthusiast. So, if you guys want to keep up, please check that calendar. And if you're interested in doing a video interview, let me know. And for the rest of the time, please, feel free to mingle.